The Global Positioning System, most known as GPS, is used to determine geographic location in several fields, such as topography, aviation, military, and most known in transportation. Its technology is now so common that cars, cell phones, and other electronic devices are equipped with a GPS. Thanks to all the portable GPS, the user can determine its exact location and move just with the GPS.
Well, also the GPS can calculate other information like speed, track, and the destination of the travel distance, the distance of the destination, hour of day or night, and more things. The basic idea of the GPS is a variable of a three-dimensional triangulation. The location of the GPS receptor on the Earth's surface is determined by its distance to three satellites. So, if we calculate from the time it takes for radio signals to reach the receiver, it is assumed that the Earth is a plane over which a x, y, and z coordinate system is superimposed, with the center of the Earth at the region on the positive z-axis pointing toward the North Pole. Now let's consider that one unit is equal to the Earth's radius. Hence, Earth's surface becomes a unitary sphere with the equation x to the power of 2 plus y to the power of 2 plus z to the power of 2 is equal to 1. The time will be measured in hundredths of a second. Now, how we calculate the distance of the GPS? The GPS finds the distance by knowing how much a radio sign takes to travel from one point to another. For this, it is necessary to know light speed, which is approximately equal to 0.47 terrestrial radius 10 minus 2 seconds.
Now, let's imagine you are an excursionist which is lost in a forest in the point X, Y, and Z at a certain moment called T. You don't know where you are, you don't have a clock either, so you don't know what time it is. However, you have your GPS device and you can receive simultaneous signs from four satellites at once, which they give you positions and times as shown in the picture 2.11. So let's imagine we have a position in X, Y, and Z, and we have a time t when the sign comes. Our objective is to solve for X, Y, and Z and t, and you can calculate its distance to the satellite in the following way. We first have to know that the sign travels with a speed of 0.47 terrestrial radius to the 10th power minus 2 seconds, and it sends in the time of 1.29 and arrives in a certain time t which we don't know, so it took t minus 1.29 hundred of a second to arrive with you. The distance is equal to the speed multiplied with the time, so we will have the following equation, which will be the distance is equal to 0.47 multiplied by t minus 1.29. And another way to express the distance in terms of x, z, and y and the position of the satellite will be, in this case, it will be 1.11, comma 2.55, and for c it will be 2.14 with the use of the formula.
So, another way to have this data is that distance will be equal of the root of x minus 1.11 to the power of 2 plus y minus 2.55 to the power of 2 plus c minus 2.14 to the power of 2. And then if we mix these two formulas, we will have x minus 1.11 to the power of 2 plus y minus 2.55 to the power of 2 plus c minus 2.14 to the power of 2 will be equal to 0.47 to the power of 2 multiply t minus 1.29 to the power of 2.
Now, if we simplify, develop, and reorder the last equation, we are going to get this equation, which corresponds to the first satellite. And if we do the same process for the other satellites, we're going to get these equations, where, as we can see, it is not a linear equation because we are missing some variables, and we want a system that has four variables, which are x, y, z, and t. So what we can do is to take each of the equations, and we are going to subtract the first equation from each of these, and we obtain the following results, which for the first equation we take 5.74 minus 2.22 x, and we obtain 3.52, and for each of them, so on and on. So for the second, we get 5.10y minus 1.42z minus 0.01t, which is equal to 2.05. For the second equation as well, we take this one and subtract of the first equation. So we have minus 22x minus 2.94y plus 0.3z minus 0.64t, which is equal to 7.21. And for the last equation, we do the same. We take this equation and we subtract this one. So we obtain 0.86x minus 3.08y minus 1.82z minus 1.22t, which is equal to minus 10.69. And with now our new system is what we are going to use to find the matrix to solve these equations.
So we did this matrix from the previous system of equations, and this matrix 3 by 5, we solve it and we get these results. This is all the process. And if we have x is equal to 2.97 minus 0.36t, y is equal to 0.81 minus 0.03t, and z is equal to 5.91 minus 0.79t. So with t as a free variable, we get this equation equal to 1. And if we substitute this equation, we get 0.54t to the power of 2 minus 6.65t plus 20.32 is equal to 0. And we get these two solutions. T is equal to 6.74 and t is equal to 5.60.
Now, with the new values we got from the last equation for t, we got the exactly two solutions, which are 6.74 and 5.6. And now, if we substitute each of the values in x, y, and z with these equations, for the first solution, we get the coordinates 0.55, 0.61, and 0.56. And for the second solution, we get the coordinates for x 0.96, 0.65, and for z 1.46, which for the second solution, it's clearly not over the earth because this value cannot be more than 1. So if so we now know this is the value we are going to use, and it also satisfies this equation, that is um, x to the power of 2 plus y to the power of 2 plus z to the power of 2, which these values to the power of 2 are equal to 0.5. 99.
So, in practice, GPS takes in mind many factors, such as the fact that the Earth's surface is not exactly spherical, hence, they need additional refinements that involve techniques such as the approximation for minimal squares.
Also, the results of the GPS calculus convert the rectangular coordinates called Cartesians to latitude and longitude, a very interesting exercise which involves other areas in mathematics.